We have here the 2013 Queensland Physics Senior External Exam. We're looking at Paper 1, Part A, Section 2, the short response, Question 7. First thing we do is we read the question. A double slit experiment used to determine the wavelength of a monochromatic light source has a screen placed 3.50 meters away from the slits. If the slits have a 0.00400 millimeter separation and the dark fringes on the screen have a uniform 3.50 centimeter separation, what is the wavelength of the light source? Having read the question, knowing what it's about, we now need to go through and we need to identify the most important information. So again, it's a double slit experiment. We're after the wavelength. It's one wavelength of light, monochromatic, and there's a screen 3.50 meters away. It's in meters to three significant figures. The slits have a separation of 0.00400 millimeters, so that's our separation. Again, that's three significant figures, but it's in millimeters, not meters. And the dark fringes on the screen have a uniform 3.50 centimeter separation. Again, it's three significant figures, but the unit is in centimeters, not meters. And so we will need to go through and make sure we have all of the measurements in meters, and we're after the wavelength of the light source. We now need to draw a diagram. So when we draw our diagram, it's a double slit experiment, so we have two slits. It's a monochromatic light, so the one light source here, and the light goes through the two slits, and there's an interference pattern, and the interference pattern here appears on the screen, and the screen is 3.50 meters away. So the length, or the distance to our screen, is 3.50 meters. The slits have a separation here, 0.00400 millimeters. So that is the separation of our slits. So that's our D value, 0.00400. Now it's in millimeters, so I need to multiply that by 10 to the negative 3 to make sure that it's in meters. The next thing we have is the dark fringes on the screen have a separation of 3.5 centimeters. So we have a central maxima, then we have a dark band, and then we have our first maxima, and then we have another dark band, and then we have our second maxima, and the same applies on the opposite side. So we have our first minima, and then our first maxima, and then our second minima, and then our second maxima. So these dark bands here are all of our nodes, and they are separated by 3.50 centimeters. So that's our delta X value, 3.50. Now, centimeters, we need to multiply it by 10 to the negative 2 to get it into meters, and what we're after is lambda. So there we go. We've gone through when we've drawn and labelled everything. We now need to use this information and decide how we're going to go about and find this lambda value. So we have a look at our formula sheet. Our formula sheet starts with kinematics, which is the first part of the exam paper. It moves on to light, which is the second section of the exam paper, and it's the questions that we're doing now. And we have a look here at our particular values. We have a value for L, for D, for delta X, and we're after lambda. So looking here, here's our formula that contains each one of those values. We need to transfer that formula onto our answer sheet. So we've got delta X equals L lambda on D. So we've transferred our formula over. From that, we now need to lock in our values to that particular formula. Now, make lambda the focus of that equation. So to get the lambda by itself, divide both sides by L. So delta X on L, and again to get the lambda by itself, multiply both sides by D. Multiplying by D, they cancel. Dividing by lambda, they cancel. Whatever we do to the right, we need to do to the left. So there's our formula transposed to make wavelength the focus. Now we need to substitute in our values. Delta X, 3.50 by 10 to the negative 2, multiplied by D, 0.00400, and that's by 10 to the negative 3, and we need to divide that by the distance away that our screen is, 3.50. Now we put those values therefore into a calculator. We have 3.5 times 0.004 divided by 3.5 equals 0.004. 0.004 multiplied by, now with our indices, 10 to the negative 2 and 10 to the negative 3 is 10 to the negative 5. Now that's in metres. Cancel. Now looking here, now that we've done our evaluation, we've got an answer here. We now need to see, does our answer make sense? Now with significant figures, we need to have the right number of significant figures. This is 3 significant figures, this is 3 significant figures, this is 3 significant figures. So we need to put this as 3 significant figures. And so I want to write that as 4.00. By 10 to the negative 5, to get it as 4, I need to move the decimal point 3 places to the right, which is 10 to the negative 3. So that's multiplied by 10 to the negative 8 metres. Right, I've got my answer now expressed in the right number of significant figures and in the quite standard form. And I now need to make sure I include the question as part of my answer. What is the wavelength of the light source? So for the examiner, the wavelength of the light source is lambda is equal to 4.00 by 10 to the negative 8 metres. With your marking scheme, this is worth 3 marks. You get 1 mark for stating the formula with lambda as the focus. You get 1 mark for substituting in the values, and then you get 1 mark for your answer being correct and to the right number of significant figures.